Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. One-Step Methods. Method of Taylor Polynomial. Taylor polynomials are a powerful tool for approximating solutions to differential equations, especially when dealing with initial value problems. The method uses the idea of expanding the solution of an ordinary differential equation into a Taylor series around an initial point. This approach is particularly useful in cases where the exact solution is difficult to find, but the function and its derivatives at a particular point are known. The method requires careful handling of higher-order derivatives and is best used for small intervals around the initial condition. Consider the following first-order IVP, where yx is the unknown function, dependent variable, x is the independent variable, fxy is a given function, and yx0 equals alpha 0 is the initial condition at x equals x0. The first derivative of the function, y prime equals fxy, and its initial value are given in the problem. This information is sufficient to construct an nth-degree Taylor polynomial. An nth-degree Taylor polynomial, Tnx of yx in the vicinity of x equals x0, can be expressed as follows, where the remainder is given as for any x equals xi, the Tn can be generalized as. Note that T1 corresponds to the explicit Euler method, and the remainder takes the following form, with. Even though the algorithm is straightforward, it does require the user to derive and supply an appropriate number of derivatives of f, which can become cumbersome very quickly. Higher-order derivatives of yx can be generated by simply differentiating y prime as many times as necessary as follows. The advantages of the method are: it is a semi-analytical method for solving initial value problems. It is an explicit method that only requires knowledge of the prior step to estimate the current step. It is capable of providing highly accurate solutions if a high-degree polynomial approximation can be derived, i.e., the order of error is n, where n is the degree of polynomial approximation. An optimal degree of a polynomial can be determined by ensuring that the remainder satisfies the desired accuracy, Rn less than epsilon, in the solution range. The disadvantages of the method are: it may diverge when the ODE is stiff or fxy is not analytic near x0 or has discontinuous points, and so on. It requires explicit expressions for high-order derivatives of fxy, which may be cumbersome or very difficult to find since the coefficients of the polynomials depend on fxy. Computationally, it can be expensive per step due to the larger number of function, as well as high-order derivative evaluations. Consider the following first-order initial value problem. Use the second and third-degree Taylor polynomial approximations to solve the given initial value problem up to x equals 1. Use h equals 0.1 and compare the estimates with the given true solution. We find the second and third derivatives using the chain rule. All derivative terms are reduced to x and y and simplified. The general Taylor polynomial with fourth-order truncation error can be written as follows. Substituting the simplified expressions for the derivatives, a third-degree polynomial approximation becomes. Noting that the following u substitution of h over xi plus 1 greatly simplifies the T2 and T3 approximations, which can significantly reduce the arithmetic operations. The initial point is x0 equals 0 and y0 equals 2, so we find the abscisses as xi equals I times h for all I. The initial value, as well as the computed abscisses, is tabulated. Computing u0 yields minus 0.1, and the approximations T2 and T3 are obtained as follows, and the results are placed in the second row of the output table. To obtain the solution for the second step, I equals 2, or specifically for x2 equals 0.2, we calculate u1, which leads to minus 1 over 11. Using u1 and y1 from the second-degree estimate, we obtain T2 as 1.6695, 868. Using u1 and y1 from the third-degree estimate, we obtain T3 as 1.6663, 862. We continue this recursive process in the same manner for y3, y4, and so on until x equals 1 is reached. Notice that the errors of the estimates from the T2 and T3 approximations are proportional to 0.1 squared and 0.1 cubed, respectively, which is to be expected. The absolute true error for T2 and T3 estimates are plotted against the independent variable x. The error increases until x is approximately 0.7 for T2 and 0.6 for T3, and then decreases asymptotically with increasing x. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.